Welcome, Amit. So this is one of those special episodes, huh?
Yeah, there used to be this concept in college, OHT, overhead transmission.
Overhead transmission. Well, people have been warned, but I can tell you that quantum computing is on the horizon next 10 to 15 to 20 years. If nothing, for our children, we need to actually learn this a little bit,
Yeah.
And what do you think about today's episode, and what should the audience expect?
Yeah, so we invited a very special guest. Her name is Sonika Johri, and she has a PhD in quantum physics, and she's spent last 10, 15 years building quantum computers at Intel, IonQ, and now her own startup. And she's trying to simplify the interface to all of this so that mere mortals like us can start getting benefit from quantum computing. And this episode was us kind of grappling with the topic, which is so hard. And like every time you try to dig more, you feel like you're left with so many unanswered questions.
I think same, I think just understanding probabilities for the first time with AI is already a new enough thing because, as humans, it is classical computer 0 or 1, but you always want to be in this, is it black or is it white? But then most of the world is not that, it's actually gray in the middle. So this just takes it to a different level of what it means to even represent state in this quantum world. You talk about parallel universe and things like that. So it's going to be a fascinating episode. It's going to be somewhat difficult to understand, like it was for me. I'm pretty sure the same for the audience. But if nothing, to immerse yourself into an area that will basically be a real breakthrough in our lifetime. To think about it, like in our lifetime, we'll see something similar to nuclear fusion, which I think in our lifetime will produce hopefully infinite energy. This one can produce infinite computing power as well. Right?
Yeah. So you've been forewarned.
You've been forewarned.
This is gonna go all over place and not be linear and.
Yeah, what do they say? Viewer discretion advised or something,
Yeah.
But let's do that. Yeah, let's take a watch. Thank you. It's great to be here, Amit. Today we have a special guest, Sonika Johri. She's joining us from Berlin. And you guys met somewhere like maybe a couple of months ago?
Yeah, actually, I was hanging out at a friend's place, and we were helping our kids build robots. And Sonika was just visiting, and we started talking, and I got really excited about learning from her about quantum computing.
Got it.
So that's the origin of this.
Well, welcome, Sonika, to the show.
This excited to be here. Yeah.
Episode number 13. So we'll see how. And it's a very difficult topic for us. We're going to talk about quantum computing, at least the basics of it, because I think it's going to take me 10 years to understand. And just in the last 5-10 minutes of an intro, I realized, wow, this is so deep as we got into the brain and maybe how the brain works and everything. And so maybe we should do multiple episodes of this as we all get to read a little bit and maybe get to 2 to 5% of what Sonika knows. So let's start there. For a little bit to know about you, Sonika. So let's start with where you grew up, and then we'll get to your undergrad days at IIT Delhi, and then your PhD from Princeton, and so on. So let's start with life at large and what attracted you to physics.
Yeah, so I grew up, as an army kid. So both my parents are doctors in the Indian Army, right? So I grew up on various army bases all over the country. But I went to high school and college in Delhi, right? And when I was in high school, I remember it was the Army Public School, Noida. And from the library one day, I just picked up a book on that explained Einstein's theory of relativity. And I think from that moment on, I just decided that I'm going to be a physicist. I'll do whatever it takes to make it work. And of course, my parents, both being doctors, they had their heart set on me being a doctor, right? But somehow, I gave the IIT exams, I convinced them, et cetera, and I ended up studying engineering physics at Delhi. At IIT Delhi. And then, I was lucky there. I had good mentors at IIT Delhi, who really told me the correct things to study, helped me get like good internships. And then during my final year, really encouraged me to apply for PhD programs in the United States. And then as well as introduced me to professors in the US that they knew, right? And so I was very lucky in that sense. And, then I got accepted at a few different schools. And then I, ended up picking Princeton. So in Princeton, I did a PhD in what is called condensed matter physics, right? And my PhD thesis was not actually on quantum computing. It was on the theory of interacting and disordered electrons and spins. Right. So it was adjacent to quantum computing, but not exactly quantum computing. Right. And at that time, when I graduated in 2014, there was no such thing as a quantum computing industry. Right. It was still pretty much a research topic. But it was just at that cusp of coming into, companies were starting to get interested in it. So just at that point, after I graduated, I knew that I didn't actually enjoy teaching that much, right? So I didn't want to be a professor. So I thought, okay, let's give industry a shot. So I went to Intel. And at Intel, my first job was kind of a combination of, research in computer vision and software engineering, right? So nothing to do with my PhD thesis. But at that first job in Intel, there was an internal company opening for a quantum computing position. It was, I think it was the first job opening in that group. They just formed that group. And I just applied internally. I emailed the hiring manager and I said, I'm really interested. I'm excited about this. And she said, okay, let's meet. Why don't you give us a talk about your research? And, even though I had not done my PhD in quantum computing, she was, she gave me a chance. So I kind of immediately, as soon as I got that offer, I shifted my group. Okay. And then I just really fell in love with the topic.
It's awesome.
Yeah.
Maybe, for the sake of the audience and even for me, explain like condensed matter physics, because obviously the last physics I ever did was maybe in my sophomore or I would say freshman year of undergrad. So it's basics for me as well. So what's condensed matter physics?
So condensed matter physics, I guess the name is kind of archaic, but pretty much nowadays it means studying the physics of, for instance, how electrons behave, in different kinds of band structures, for instance, right? Or, how magnetic materials behave, when spins are strongly interacting, right? So pretty much, do you know the idea of emergence?
You'll have to explain that.
Yeah. So what it means is that in physics, we have this concept of when there is a system with a lot of different degrees of freedom, by which I mean it can be a lot of electrons or spins, if you know what spins are, right? You can imagine them as tiny magnets, right? So when there are a lot of degrees of freedom that are strongly interacting, you can start to see new phenomena emerge that you would not get when, you would not expect them to emerge if it was just a collection of parts. So it's kind of like the sum is more, the whole is more than its parts, right?
In fact,
so it's a study of
LLMs these days, so at least
comes from there.
Comes from there, I guess.
Yeah, so it's a study of these kind of phenomena. So, and for instance, I studied specifically what's called the fractional quantum Hall effect. which is, this kind of phase of matter that emerges when you have electrons in very strong magnetic fields at low temperatures. And, these effects are often, they arise from the quantum nature of electrons, right? They would not happen if you had just a classical description of, charges moving around in a solid. You really need the quantum picture for those.
So maybe explain that. What is the quantum nature of electron?
So in this case, it really means, first of all, that an electron is not just a spherical charge that's buzzing around, right? You really describe it by a quantum state, right? And it does not obey Newton's laws or, classical Maxwell's laws of electrodynamics, but it obeys the Schrodinger's equation, right? For the evolution of its wave function. And the second thing is that it can get entangled with other electrons. So you can have a quantum state that is not the quantum state of one electron alone, but the quantum state of a large number of electrons, right? And in those instances, you can the physics of it is very, very different than the physics of individual electrons, right?
You were asking?
Oh, I was asking, are your parents happy that you made it to be a doctor?
I hope so. Yeah.
Just a different path.
Mm-hmm.
My wife is a physician, so we joke that I'm the fake doctor in the family.
I see. Yeah.
Amit did his PhD at UT Austin too. What, 2003, 2004?
Yeah, 2003.
Interesting.
Yeah.
So we are at least barely scratching the surface of quantum right now.
Mm-hmm.
Maybe we should explain a few of the basics of quantum. So maybe we should introduce the notion of qubits and talk about qubits a little bit and how they can be superimposed states. Talk about superposition. So maybe Amit, I'll let you actually handle it.
So we will go into the science of it, but maybe it's more interesting we start outside in a little bit.
Sure.
Right? Tell us maybe why everyone should be excited about quantum computing. Where does the future lie? If, let's say, all the bets that we're making pay off, what does the future look like?
Yeah. So I would say, despite all of the progress in classical computing, right, whether it's different kinds of, just whether it's just the sheer number of transistors you can fit onto a chip, right, or innovations in architecture, right, like using GPUs instead of CPUs, or innovations in algorithms, software. Despite all of that progress, right, there are some problems that fundamentally are extremely hard to solve on classical computers, right? And some examples of problems like this are, for instance, in chemistry, right? So if you want to model nuclei or molecules, sorry, not nuclei, but if you want to model atoms or molecules that have a large number of interacting electrons that affect their chemical properties, right? Or you want to model, let's say, the chemical properties of even larger molecules like proteins, or want to do ab initio material science, right? Those kind of problems, fundamentally, no matter how much progress on algorithms you make, right, those kind of problems will remain very, very hard to solve on classical computers, right? And so these.
Sorry for the interruption, but why is that? Is it because the number of states that we have to capture exponential too fast?
Exactly. So it's like, I said before, right? For instance, when you're modeling electrons, right? If you're modeling a system of many electrons, right? You then you cannot describe them individually anymore. You really have to model what is called the many-body electronic wave function. And there, the number of states grows exponentially with the number of electrons, right? And so, in some cases, you can have an approximate description of the state, right, in a much more compact fashion. But for many important applications, that is no longer possible. And you really need a description of the state that that is able to scale exponentially with the size of the system. And for those kind of applications, quantum computers are presented as an alternative paradigm to classical computers, right? Now, of course, when we think about chemistry, there's kind of there's kind of an obvious reason why quantum computers would be good at chemistry, because chemistry is hard because you're describing quantum particles also, right? And so then it's naturally you can map that. There's a natural mapping of electrons onto qubits, say. But other than that, there are also other areas such as optimization and machine learning, right, that people have come up with quantum approaches where for certain problem classes, you can have a quantum solution that can outperform classical solutions. And some of these approaches are kind of rigorous, well proven, and some of those are heuristically people show that you can have some quantum advantage. So yeah, there are many problems, right? Whether in chemistry or in optimization, you think of all this logistics, right? Or in AI, you think of how these large language models are so power hungry, right? That they're making unsustainable demands of the world's energy resources. So because of all these reasons, we think that quantum computers can make a difference.
Maybe what you're saying is that nature works in a certain way, physics works in a certain way, which is around these electrons that actually are interacting with other electrons and so on. But the way we have done computing for the last, let's say, 80 years is probably unnatural. And now computers will probably be more resonant with nature.
That is actually one very good perspective on it, right? Because nature is not binary like this, right? It doesn't work with zeros and ones. Never, right? So quantum computing is one of the new unconventional at the moment approaches to computing. People also are looking at thermodynamic computing, and I've even heard of DNA computing, right? So there are all these different approaches that are not based on kind of this paradigm of digital zeros and ones, right?
It reminds me of Bhagavad Gita a little bit. There's no black and white. There's all gray in the middle. It looks like there's a lot of that goes on in computing as well.
So
go ahead, please.
Let's say that we get the million qubit computers or 10 million qubit computers, the scale that we can dream of right now.
Mm-hmm.
How does the world change? Is it that drug discovery certainly becomes substantially easier and you can just do simulations and know these drugs will work? Or obviously crypto is one place where things
Yeah, so I think it's so hard to predict, but I can say some concrete things and some speculative things, right? Concretely, right, if you have on the order of millions of physical qubits, which translates into maybe say tens of thousands or hundreds of thousands of logical qubits, it means that encryption will be broken, right? So no longer will protocols like RSA work, right? So that of course is a negative impact, right? It means that all of our security is threatened, and people better get ready for that. But on the positive side, yes, if we really have quantum computers at that scale, a lot of chemistry, a lot of material science will become, there will be major advances in those fields, and then kind of all the downstream effects of that, in biology and chemical industries and pharmaceuticals, right? A bit more speculatively, I can say that it may be possible to train quantum AI, right? Quantum versions of intelligence, which may be extremely different from classical intelligence, right? And so far, I can't say anything more concrete than that, other than, that we're just beginning to understand what that might look like. right? And of course, my company is directly not working in this area, but people also are very hopeful for using quantum in optimization problems or in solving certain kinds of differential equations.
Sonika, we didn't finish your background completely. So after Intel, you did go to a company called IonQ for many years.
Yeah.
Maybe do explain a little bit what the company was doing and what breakthroughs did you folks even achieve, and then we'll talk about your startup as well. So let's start with what happened at Intel and then what happened at IonQ.
Yeah, so at Intel, I focused. So I kind of I was the first hire in that group, right? And at that time, there weren't I would not even call them quantum computers. There were systems of 2 or 3 qubits, right? Like 4 qubits, five at most. And what I focused on was figuring out what kind of demonstrations could you do with even 5 qubits, say, right? So you could run a little, calculation of a little condensed matter model, let's say, or just let's say a little optimization problem, right? So just figuring out, okay, you have a target application in mind, and of course you don't have enough qubits to actually do that application, but let's design a little algorithmic prototype and figure out how do you compile that algorithm step by step into something that can be run on the chip, right? So kind of building that first prototype stack where you go from being a user of a quantum computer and you design the software that can actually compile that code into something that the chip can run. And then you work with the people who actually are operating the chip kind of manually to run it and read out the results. Right. So I've worked on several projects like that and also worked on co-design between the quantum hardware, software, and applications. And then while I was working there, I had also done a couple of projects with IonQ. Not with IonQ, with one of the co-founders of IonQ, Chris Monroe, who was a professor at the University of Maryland at the time. And then he called me up one day and said, Sonika, I want you to come to IonQ. Right. And we negotiated, at that time I didn't really want to leave, but then, after about a year, I was ready. And so I went over there to IonQ, and over there, I started their quantum applications team, right? And I hired that whole team, and I think by the end, we were about 10 people when I left. And we worked with all of the customers and users of IonQ quantum computers to help them figure out how they can use the IonQ systems to get the best possible results for their application areas, right? And so,
what was IonQ developing? What was the product?
Yeah. So IonQ is a developer of trapped ion quantum computers, right? So trapped ion quantum computing technology is based on using lasers to create an optical lattice. I don't know if you can picture what that is, but use a bunch of lasers to create kind of a lattice where you can trap ions, right? And then you again use those lasers to do quantum operations, which are able to, let's say, put the ions in superposition and entangle them, right? In other words, to kind of manipulate them as you would qubits, right? And so they had, of course, at that time, they had their very first generation of systems, right? I think it was it 7 qubits? No, sorry, it was 11 qubits at the time, right? In 2020. Right. And even on that 11 qubit system, we managed to run a lot of different kinds of prototype applications. And, our team worked with, large companies like Hyundai or, Airbus, like large companies, and also research groups at universities, as well as, students who wanted to use the system.
And really, what's the life cycle look like? Like, suppose you have this 11-bit quantum computer. I have a problem statement. Like, tell us about how you think about the application. How do you compile it? How do you run it? Like, what's that sort of meeting of the two sides?
Yeah, so for instance, I can tell you about this one application we kind of one project we did with the Fidelity Center for Applied Technology, where the goal was to build a generative model for stock prices, right? Let's say you want to model the stock prices of Microsoft and Intel, right? So that's what is called a multivariate distribution, right? So you're not just modeling one variable, right? You're modeling how two or more than several variables change together. And you want to use that model that, it's a generative model for those stock prices. And you want to feed that into something else, right? Something else that makes decisions about how to trade, right? So for that, in classical probability theory, there's this object that's called a copula. I don't know if you've heard about it, but it's an object which people use to model these multivariate distributions. So what me and my team did, we came up with a quantum version of a copula, right? So we did some design, right? We designed a quantum state that was similar to kind of what people use classically. And then we figured out how to create that quantum state on a quantum computer, right? Like how to implement it on a quantum computer, right? An algorithm that can create that state. And in this case, the algorithm was actually a quantum machine learning algorithm, wherein you had in quantum computing we call it an ansatz, but really it's the equivalent of what classical machine learning people might call a neural network, right? So, but we had this kind of quantum model which had some free parameters that you could train, right? And so we trained this generative quantum model that on the stock prices of that we just took from some standard data set between a couple of years, and then we first trained it on a quantum simulator, which is a classical version. It's trying to emulate a system of qubits. So we first trained it on a simulator, understood how the training works, scaled it up to, I think, 8 or 10 qubits. And then once we kind of had this preliminary design and kind of numerical study done, then we kind of launched it on the quantum computer itself. And you could see the quantum machine train, and it was pretty cool. Yeah.
I was just visualizing like the way punch cards were back in the day. Like you're going to get a bunch of lasers. Now you can go and evaluate what the output of that is going to look like or something, That's
So actually it's not quite punch cards, but that is one thing that we need to make a lot of progress on. So just like, you don't program your laptop in terms of the transistor voltages, right? Right now, when you program a system of qubits, really, no matter what quantum software language you go to, pretty much ultimately what they make you do is state what operations on individual qubits you want to do, right? Like put qubit 5 in superposition, entangle qubit 5 and qubit 7, right? Entangle qubit 7 and qubit 2, right? So so this is called quantum circuits, right? This is the quantum circuit abstraction. But one of the things I hope we make a lot of progress on in the coming years is increasing the abstraction level at which you program quantum computers. And this will happen, right? Because so far, if you have 11 qubits, 20 qubits, you still can do it like this. But once you have 100 qubits and 1,000 operations, you can no longer program them one by one, right? You need another layer of abstraction, right? And then the compiler generates these low-level operations for you. And increasing that level of abstraction actually also increases the level of reasoning about it, right? Like the way you reason about quantum states and quantum control and that I think will also help people come up with new algorithms if they're not just thinking about low level things. Then
Yeah. I interjected.
Yeah, it's so many questions. But this is very fascinating. So, at the end of the day, I assume there's no notion of a clock in a quantum computer, right? Like or is there, like you set certain inputs and then you read the outputs and then you do that in a repeated cycle? Like, can I think of this as a much faster combinational logic circuit or?
I'm not quite sure of the question, but maybe, so when you start off a quantum computation, right, you do what is called initialization. So you initialize all the qubits, let's say, in the 0 state, right? So you have a definite starting state.
Mhm.
And then you have let's just say quantum circuit, which is kind of telling you, what operations happen on individual qubits, right? And in the end, you do a readout, right? So you read. So when you start out, the qubits are in a classical state, right? They're all in, let's say, in 0. During the middle of the computation, they are in a superposition. So they're in quantum state. It's not classical. And then when you read it out in the end, then you collapse that superposition. You collapse the quantum wave function again into a classical state. And in the end, you're reading out concretely zeros and ones, right? And then sometimes, sometimes at the end, what you want to read out is the probability distribution. So you run the computation over and over to get, to read out the distribution. There are some variants of quantum circuits where, I don't want to go into so much detail. People do this mid-circuit measurement where instead of just reading out in the end, you read out in the middle few of the qubits. And, there's certain techniques why, there's certain reasons why you might do that as well. And one important thing to keep in mind is that all quantum, other than this measurement, every quantum gate is reversible, right? So that's an important distinction from classical computing, that quantum gates are always reversible, and that gives it certain properties that are very different from classical.
And say more on that, like what does reversible mean?
So reversible here is also different from classical reversibility somewhat. Reversible here, in a mathematical sense, it means that the mathematical way to state it would be that all the quantum operations other than the measurement are unitary in nature. So that's like a technical property of a transformation. But practically it means that everything is reversible, right? So any operation that you perform, the inverse of that operation also exists. So if you run something this way, if you run it backwards, you'll get back what you put in. And then a second thing is that for the unitarity, it means that probabilities are conserved, but that's kind of a more technical thing.
In other words, no information is destroyed in the process.
Information is except at the measurement step. Exactly.
So in math terms, if I have range,
if I add A and B, I get C. Now from C, I cannot go back and say what was A and B.
Yes,
but it's a requirement in quantum computing.
Yeah. So for instance, if you have a quantum adder, right? Let's just say you're adding two bits together, right? You go A and B, and then always at the output, you would also always have two outputs as well. Maybe one is storing A plus B and one is storing A by itself. So then, then you can reverse it, right? If you have A plus B and A, then you can reverse it. So even if you just want A plus B, you'll still be storing that A somewhere else.
And what's the importance of this reversibility? Like, does it have anything to do with the way you said, you're going to have to repeat this multiple times to get the final states? Does it have anything to do with even back propagation, for example, in neural networks? Like, are we talking about things that are even related?
No, not really. I mean, the unitarity is just a physics property, right? Like, because the Schrodinger equation, right? That's just how our world is, right? Our world is unitary evolution.
So
Yeah.
you have to break it down for our audience as well. For me, in
Okay.
particular, what is unitary evolution?
Well, unitary evolution is well, I mean, I can just describe it very technically, right? Like, if you're, if the matrix that describes your evolution, let's say it's U, then just mathematically, it means that U dagger, right? So the adjoint of U times U is equal to the identity, right? That's just the most compact way you can state it, right? So this unitary evolution is not something we actually kind of argue with too much. Like, we take it for granted, but it enforces certain properties on the computation, and it also gives it certain properties. For instance, like you were talking about in machine learning, right? What could be the use of it in machine learning? So one thing is, if you train a quantum model, right, it means that you can run it forwards and backwards, right? Right. So you can run U or you can run U dagger, right? And so one of the things, for instance, my company is working on is, in certain instances, if the model forwards, right, if you run it in the forward direction, is a classifier, under certain circumstances, if you run it backwards, it can be a generator, right? So you can run the model forwards or backwards, right? So those kind of structures are still kind of emerging, right? It's very early, but yeah, it's what makes it different from classical. But I hope that was not too technical. Like,
That's why
I don't explain it so many times.
This topic has been done multiple times. But I think you're doing your best to explain, but you realize how classical my mind is right now, and I just love the word classical. It looks so fancy, but it looks so arcane as well at the same time, given where things are headed in the next 20-30 years. Amit, say.
Yeah, I do use when you're in quantum computing, even the latest LLM, you'll say, oh, the classical machine learning.
So maybe it's a good time to get into the physics, the how of it, and the theory of it. And the best way that I know how to understand a complex topic is maybe go historically, like what was invented first and what was invented after, and so on and so forth.
Mm-hmm.
I read somewhere that like even like back in the day, Feynman hypothesized that there could be something like a quantum computer that could result in some exponential gains. Is that a good starting point, or maybe you want to go all the way back to like double slit experiment and how we started thinking about quantum physics?
Yeah. I mean, we can start wherever, right? But it's quite interesting to me, right, that quantum physics was actually emerging in a time where the world was in a lot of turmoil, right? At the turn of the century, and then of course, it really started with the black body radiation puzzle, right? So classical physics could not explain the spectrum of a body at let's say you have an object at high temperature, right? And it's emitting radiation. Classical physics predicted that radiation would increase exponentially with frequency. At low frequencies, it would go up exponentially. and that didn't low frequencies or low wavelengths, one of the two, it would go up exponentially, and then that didn't happen. So then, kind of people came up with alternative explanations of how that of why that distribution didn't look as classical physics had predicted. And then from there, of course,
you heat up a metal or something, and
yes,
then
exactly,
into a prism, and then you measure the intensity of light at different places.
yes, exactly. Yeah. So a straightforward experiment that you can do, right? But you cannot explain it with classical thermodynamics, right? And so, and then of course Einstein came up. Einstein also contributed. He studied the photoelectric effect. In addition to relativity, he had also all this other work, right? He was one of the originators of quantum physics as well. And then fast forward many years, right? There was Feynman, right? And kind of his motivation in proposing quantum, computers based on the principles of quantum physics was actually that it was very hard to explain the behavior of quantum particles like electrons, right, with classical computers because of this exponentially growing state space issue that we had discussed earlier, right? And so I think that's as far as he went. He thought quantum computers could be used to model physical systems of quantum particles. But then a few decades later, of course, I think people in computer science departments mostly started studying it, or math departments kind of started studying this topic at a more abstract level. And then I think it was Peter Shor. He came up with Shor's algorithm, which showed that you can factor a number on a quantum computer exponentially faster than you can do it on a classical computer, right? And that's where kind of, I think, the modern quantum, modern approaches to quantum computing kind of started. And this was, of course, the theoretical development at the experimental or hardware level. People were lots of experimentalists were kind of improving in their abilities to create small superconducting circuits, or studying the physics of atoms, studying the physics of electrons, right? And kind of improving the experimental capabilities around, like I said, creating lattices from lasers, things like that, right?
And when did you move from quantum mechanics, quantum physics to the word qubit? Like when the word qubit invented?
Oh, that's a good question. That I don't actually know. Yeah, I don't. Qubit. Who invented it? I don't know.
Before Peter Shor, or
I don't know. I actually don't know.
What was the motivation? Like, I'm sure there was a motivation because we were probably using bits like zeros and ones. And
yeah, so it's like quantum bit. Yeah.
So it could only be in one state, 0 or 1, but not both. And then they said, no, there's a way in which a quantum bit can be in both states at the same time. So maybe explain that proposition, whatever the qubit invention was supposed to capture.
Yeah, so like you said, a classical bit is 0 or 1, right? So it's the smallest unit of classical information. A quantum bit can be in what's called a superposition of 0 and 1 at the same time, right? So it's like, you might have heard of Schrodinger's cat being both dead and alive, right? It's exactly the same thing, right? So what does the superposition actually mean? So it means that you let's say you have a qubit in this quantum state. It means that you have some probability of measuring it in the 0 state and some probability of measuring it in the 1 state. It's not definitively in one or the other. And so that's one thing that distinguishes a quantum bit or qubit from a classical bit. Another thing is that ability of quantum bits to get entangled with other quantum bits, right? And so this is the other big thing that people talk about: entanglement, spooky action at a distance, right? There's all this kind of lore associated with it. But what it means is that if you have 2 qubits, right, you can be in a superposition of 4 states, 2 to the power 2, right, at the same time. If you have 3 of them, you can be in a superposition of 8, and so on. So if you have n quantum bits, you can be in you can have a state that is 2 to the n in size, right? And that is not approachable classically. Like, you cannot model that. You cannot describe an exponentially growing state on a classical computer, no matter how many GPUs you have, or when you are, about 64 or so qubits. No matter biggest supercomputer in the world, anything you do, you just cannot describe it classically anymore. And there people always like come up with, we made this kind of tensor network algorithm that can now do 64 qubits. Let's say, well, then you just increase by 1, you go to 65, and it no longer works, right? So.
So let's spend a little bit of time here. Like, I always have trouble with this. So in some ways we're saying that, so let's say if I have 64-bit classical storage, right? So it just picks one of the 2 to the 64 possibilities and stores it. And when I manipulate, I'm just manipulating one of those 2 to the 64 possibilities through an AND gate or whatever, right? But what we're saying is that in quantum, all 2 to the 64 possibilities simultaneously exist. So when I apply a quantum gate on that, I'm manipulating 2 to the 64 quantities almost simultaneously. Like, I can't observe all of that. Like,
exactly,
it needs to be collapsed into some classical state to be measured. But in between, I'm manipulating 2 to the 64 numbers simultaneously. Is that right?
Exactly right. Exactly right. Yeah.
Wow. That is something. The fact that in classical computer, first of all, you can store 2 to the power 64 variables.
Yeah.
You need a massively large amount of RAM to do that. And even in that case, you have those many variables, so there's no way you're algorithmically thinking about those many variables at the same time. In this case, you have one sort of state that is in 2 to the power 64 probabilities.
Yeah, so the probability distribution spans all those quantities, and you can manipulate that probability distribution by applying quantum gates, which is simultaneously kind of working on all of that. Now, the problem is that you cannot just go and read one of those states. It will always remain a probability distribution from which you can sample. And that's where quantum algorithms come.
I'm going to ask a very, maybe a stupid question, because my mind has barely moved to deep neural networks for the first time. I'm like, okay, now I understand probabilities of the end state, the output layer or something, So for the first time, I'm moving from classical thinking to probabilistic thinking. Obviously, this takes me to a completely new way of thinking about probabilities and so on. Is it like the natural way? I mean, first of all, are deep neural networks a baby step in this direction? Because we started thinking about output layers and probabilities of output layers, and the fact that if you think of this one thing as a gate, like the network is a gate, is it actually moving in that direction where eventually quantum computers will be?
So certainly it is the case that when you think of, let's say, generative AI, right? What that is that the model is learning a distribution over possible answers and then picking the best possible answer, right? And with quantum states, there's a very natural way, like it is a probability distribution, not artificially creating something, but with classical neural networks, basically you feed it a bunch of random numbers at the input, and then the output, it generates your target distribution, right?
Mm-hmm.
With classical, with quantum neural networks or quantum learning models, it naturally can encode a distribution, right? The question is, can you create an architecture? Can you train the distribution in such a way as to make it useful, right? So the ingredients are all there, but we are still learning how to kind of engineer those for useful applications.
Mm. So naturally, what we have done in the last, let's say, 10 years, I would say, with LLMs and deep neural networks, this is an obvious sort of step towards finally getting to these kind of quantum computers. Like what we are doing with massively large number of NVIDIA GPUs. Is there a brute force way to mimic nature, and eventually we'll get with by using quantum computers for the same thing?
Yeah, I think, the answer will depend on who you ask, right? So if you look at, and now, I'm kind of, I don't know if you want that much detail, but, there's certain kinds of quantum researchers who work on things that, that are only mathematically provable, right? So, they don't advocate for doing anything unless you can prove a theorem about it, right? And there are no such theorems yet that show that with the quantum approach, you can model a distribution that is similar to what an LLM can model, right? There's no efficient way to train such a model, right? But on the other hand, even with classical machine learning, right, there's no proof that you can train ChatGPT, right? It's just that when the computational power and at scale, a big computational power became available at scale, people tried things and they worked, and they kind of engineered their way into improving and improving and improving. And I think, my approach with quantum computing is also the same, right? That every year we have more powerful quantum computers, and let's develop the techniques that kind of enable us to train large quantum models, right? And as you mentioned, that analogy of the probability distribution does exist, right? And instead of trying to prove theorems about it, let's just try it out, similar to how we did it classically. But the analogy exists, yes.
So, I'm still kind of trying to wrap my head around this. So a qubit is something like maybe an electron spinning one way or the other, right? And if it is definitely spinning one way, then it's a 1. If definitely spinning the other way, then it's a 0. But
well, with the caveat that it's not necessarily an electron. So electrons are actually kind of more complicated than qubits because they're fermions, right? So in addition to having this spin degree of freedom, right, 0 and 1, they also have another property because they're things called fermions. So they have some additional statistical physics considerations. So usually qubits are simpler than fermions. Like people use atoms, right, or ions. Or they use a little superconducting loops to create a qubit. And a qubit is basically any particle where you can isolate two levels, right? And you can ensure that it's only controllably going between those two levels. And that's a qubit. Actually, there is some work where people are also working on qubits, where there are 3 levels, right? And so they're trying to figure out how to build a system where you are, changing the state of the particle between 3 different levels, 0, 1, 2, let's say. But though that's more like early stage.
So, you said you want a particle that you can have in 2 states and no more than 2, and that's a qubit. How does it actually stay in both states at the same time?
So, it's so so what I mean is that you can control where it is between those two different states. So it can be in just the zero state, called ground state, or it can be in the one state called the excited state, let's say in physics terms. But let's say let's take the example of the spin, right? So if the spin is pointing up, it's in zero. Spin is pointing down, it's in one. But if it's pointing like halfway between the two, right? Roughly, classically you can make that analogy, right? So it's not zero, it's not one, but it's pointing like this. Then, when you measure it in the zero or the one direction, it will sometimes give you zero, sometimes give you one, and that's the superposition, right? So it's not up, it's not down, it's like halfway. That's how physically you would model it.
So this is where I think it may be good to introduce the concept of phase and interference, because without that, the quantum computer doesn't work, right?
Yes. Okay. So that's an important thing, right? So when I say that it's when you say it is in a superposition, right? Let's say it's in the state alpha 0 plus beta 1, right? So that so alpha is some variable, right? And beta is some variable. Then those alpha and beta don't have to be real numbers. They can be complex numbers, right? So it can be a magnitude times a phase, right? And when you measure it, the phase is lost. But during the computation, before you measure, that phase is really important. When you do the different quantum operations, that phase can make a big difference. It can lead to constructive or destructive interference. And actually, in many applications, you have this probability distribution, right? And what you're trying to do is manipulate that probability distribution through this destructive interference to kind of reduce the probability of getting a bad answer and increase the probability of getting a good answer, right? So the algorithm design is trying to do that.
It may be helpful to define phase in terms of wave equation and like go back to maybe classical definition of phase and then quantum definition of phase.
Yeah.
And maybe while you're thinking, Sonika, maybe Amit,
Yeah.
explain, because you also have a layperson's view of this, but it's going to be good for the audience, including for me, who is way more layly than anybody else out here. So explain to me, like, when you were reading about phase and interference, how helpful was it?
So if you think of like a classical wave, like sound wave or a string vibrating, right? You can describe the position of the wire as a sine function or cosine function, right? So you say that the position of the wire, how far away from center, is sine of t, is time elapsed, times frequency, right? So at phase 0, it's kind of at the center. At phase 90 degree, which is like quarter of the frequency, it's at its highest, and then it goes down again at 180, and then at 270, it's at the lowest point it comes. So that's the sort of classical definition of phase of a wave. And this is where, if you remember the standing waves, that like one wave is going this way, the other one is going this way. When they, if they're perfectly aligned, then the amplitude goes up twice, the energy goes up 4 times. But when they're perfectly misaligned, then they completely cancel each other out. And so when Schrödinger described quantum physics, he basically said that everything is defined by this wave function. So instead of electron being a point mass, it can be described by a wave function, and the amplitude of that wave defines the probability. So if the amplitude is high, then there's a higher probability that electron is there. If the amplitude is low, then there's low probability that the electron is there. So when you sample and try to observe where the electron is by putting a screen or something in front, by many, many measurements, you can get the sense of the probability distribution, but that only tells you half of the story. It just tells you the amplitude part. It doesn't tell you the phase part. The only way you can see phase is by seeing two different Schrodinger's wave equations getting added. And that's where superposition happens, where you will see that, like, let's say you have electron coming from one slit and another slit. If you just measure the probability distribution of this thing, you will see certain pattern. You just measure probability distribution of this thing, you'll see certain pattern. In a classical world, you would expect those probability distribution to add up when you let electrons go from both the slits, but that's not what happens. What you see is like bands of high probability, low probability, high probability, and that's because the waves are meeting each other at where it's low. They're basically canceling each other out. There's no equivalent of that in classical physics. And this is what kind of made people, so when this double slit experiment was done, where you're firing electrons from two beams, and you look at the intensity of registered electrons over a period of time, this could not be explained in any way with classical physics. And in my mind, this was kind of pivotal moment when things started to change in terms of our understanding of the world.
And I know you introduced the word fermion like maybe 10 minutes ago.
Well, actually, I just want to add something to that, right? So this is like, this picture, right? It explains, right? Like, what do we mean by the quantumness of a single particle, right? But there is another level of complication where all of this physical intuition in analogy with classical waves, right? Once you have many entangled qubits, many entangled particles, then you lose even that physical intuition, the analogy with, waves interfering like that. That there's not really any straight analogy with like entangled system of 50 qubits anymore.
Of course, you folks probably use the word entanglement tens of thousands of times a month, but for people who have not appreciated what entanglement means, like the fact that you took two of these things, then you moved them far apart, and when looking at the state of one, you understand the state of the other. How do you intuitively think of the word entanglement? In real life, like how should we think about two qubits being entangled? How does it even happen?
Yeah, I mean, so, first I'll say a non-accurate, like an inaccurate thing, but it'll help to explain, what the accurate thing is. So imagine that you're a person who always has their socks after the laundry well sorted, right? So you have socks that have many different colors, but always, your blue socks are with the blue socks, red socks are with the red socks, etc. Right? So now, if your friend sees your left leg has a blue sock, right, then he will be able to infer that your right leg also has the blue sock on, right? So this is what people mean when they say that, whenever you measure a set of entangled particles, right, if you see one, immediately know what the other one is as well. But where the analogy with the socks breaks down is because it's not because it's not that you wore a blue sock. It's almost like you wore a superposition. If you were wearing a superposition of a blue plus red sock, right? Even then, if your friend saw the blue sock, right before the measurement, there might be a superposition, right? Of blue plus red. But as soon as one of them is measured in blue or red, the other one immediately collapses. in blue or red as well, even if there's no contact between them anymore, right? So what that means is, right, you can have 2 qubits in a state of 0, 0 plus 1, 1, 0, 0 and 1, 1. And if you measure one of them in 0, the other one is in 0 as well. If you measure one of them in the 1 state, the other is in the 1 state as well, right? Now, sometimes, Einstein, I think, many people have kind of think that this means that you're violating the theory of relativity, right? That this is spooky action at a distance. It means that you are communicating faster than the speed of light, etc. But rigorously, you can show that that's not possible, essentially. But it is very non-classical, right? And I think a couple of years ago, the Nobel Prize in Physics was actually given for the experiments that tested, established that this property of entanglement.
I was trying to prepare for this podcast yesterday, and it took me to one of these other podcasts out there about the EPR paper and Bell's inequality paper, and then the Nobel Prize was actually given in relation to the Bell's inequality paper, where they're trying to look at entanglement either as a non-local versus a hidden parameter, the fact that one of them knows about the other kind of stuff. And it was just fascinating how this professor at MIT, I think it was, I'll remember the name, but he was like, there's so many people who have completely misinterpreted Bell's inequality paper. So even the press release of the Nobel Prize had it wrong. I'm like, oh gosh, like imagine if those people who've been working on it for decades get this thing wrong. I'm okay. I know I suck at these things, but I'm okay. So how does entanglement help?
Well, just to comment on that, right? I think at the heart of that is actually, we don't really know what's happening, right? Because, in physics, there is this one school of thought, it's called shut up and calculate, right? Which is, you have these equations that work, that have been tested again and again experimentally, right? So don't think too much where they are coming from, what's happening. Just use them, describe, systems of electrons, spins, use it for designing quantum computers, et cetera, right? But at the same time, in the back of your mind, there is this question, what is happening when you actually measure, right? Why does this quantum particle, measurement just means you read out a photon, you exchange a photon, or it can mean something else, you measure a current, something like that. What happens? Why does that quantum particle suddenly become classical? Are we somehow getting entangled with it? There's just this mystery, right? Like, is there such a thing as objectivity? Maybe, maybe there's no such thing as objectivity, right? It's all relative, right?
Actually, I'm beginning to question myself now.
Yeah. So I think the reason that it's often, it's so hard to explain is because scientists also don't really fundamentally understand it. They can calculate a lot of things, right? And you can do a lot of engineering with that. But often the paradigm shifts come when you get out of the mindset of shut up and calculate and start thinking about...
It's happening with AI as well. In many ways, we don't know how they're working. We just, when you look at the measurements, like, oh, that looks real. So it must be doing somewhat real things,
Yeah, because there's this one approach, right? Just train bigger and bigger models. Just keep doing that, right? But then, of course, right, you also have to start questioning, right? What is it actually learning? Is it just interpolating, or is it actually capable of reasoning, right? And I think that's where the paradigm shifts come in. And
coming back to entanglement, does the one way that I try to think about it is parallel universes, that we're basically
the multiverse theory. Yeah.
We're constantly getting a sample of one of the parallel universes. And
you just made this simple last 1 hour into something a little bit more complicated. I thought it was a simple world that we were living in. Now we're living in a parallel universe. But keep going, because this podcast has no limits.
So, like, one way to think about it is that, so if, let's say, if I do a toss here and you do a toss there, and let's say there are many, many versions of this universe going in different universe, I get head, you get tail, you get head, I get tails, and so on and so forth. But and they're not correlated at all, but somehow an entanglement happens in every one of those universes. If I get a head, you get a tail, or something like that. And we don't understand why that happens. But
and what are the implications of that on a 100 qubit quantum computer, in the sense that, we can now model things in unique ways? Like, what is the big deal with entanglement and computing?
Yeah. So there were two things, right? One is about the parallel universes, right? So that is like, it's, again, we don't really know, right? And we don't have any way to test it, right? If there were parallel universes, how will you test it? Right now we don't have good ideas around that, right? Or maybe it is just that, like our notions around objectivity, that's just not that's not how things function, right? So we don't actually know. So there is, but I hope that there will be some progress, and I hope that with quantum computers we will be able to perform certain kinds of experiments.
Sonika, I'm going to get into the realm of something really funny here, but when I was watching this entanglement video yesterday, it reminded me of my twin girls. I'm like, is it possible that they're entangled? Because they're identical twin girls. And I'm like, the more I watch the video, I'm like, is there something we said about entanglement between the two of them? And I don't want to take this discussion in that direction, but it's that sort of meta in my head right now. Like, what does it even mean to say that they're entangled?
I mean, the thing is that if at a quantum level, if two objects interact very closely with, how do you create entanglement, right? Like, I think you asked, how do you entangle two things? You just let them interact. If you write the equation, if two spins interact with each other for a certain amount of time, or two electrons or whatever, right? If two objects interact with each other for a certain amount of time, and then you take them apart, they are entangled, right? So entanglement is created through close interaction. So physically, like physics, from on the physics level, right? Like if two electrons are so close to each other that they have some Coulomb interaction, right? So the Coulomb, the Coulomb force emitted by one is affecting the other, right? Then they get entangled physically, right? And there are different mechanisms. So if they're electrons, maybe they're interacting through Coulomb interaction, right? If they're spins, they have some magnetic interaction, right? So there's some fundamental force.
Looks like their interaction changed their habits, and now when they're even far apart, they're habituated to that.
Yeah. So at a macroscopic level, we don't know quite how to describe this, right? We can write down what the equation for the interaction is if it's like small objects. But whether, and most theories of physics hold that at macroscopic levels we don't observe quantum effects anymore. But our knowledge of the universe is incomplete, right? We don't know really the fundamentals of even how do you measure a qubit? Even though we are building quantum computers, we don't quite understand them, right? So who knows how. I choose personally to keep an open mind about how quantum effects might emerge at macroscopic level, whether in our brain or human society. But that's extremely speculative, right? I don't want to make any concrete statement about that.
But there was a part that talking about entanglement and these, let's say, 100-qubit computer. Like, how does it help computing?
The way it helps, the implication of that for large number of qubits is that it is only when you entangle something that you can get this exponentially large state space, right? So if you don't entangle them, then you will only have like you can describe it as you can describe each of the particles individually, right? They have their individual identities. Once you entangle them, then it's really like this many body, I call it a many body quantum state, where essentially each particle almost, you can say, does not have a unique identity anymore. It's part of this exponentially large state space.
And maybe this is where, Amit, you were saying waves, if you were to think of waves, it'll help. Because otherwise, if they're not entangled, then 100 qubits could look like 200 bits or something, at most or something. But because they are actually entangled, you have 2 raised to the power 100 states at the same time. Is that the way to think about it?
So I think in some ways, entanglement, the way you entangle them, reduces the state space to the interesting parts where sort of we're trying to do computation. So if 2 electrons are entangled, not entangled, then the spin could be up, down here. If they're entangled, then essentially we're saying that if this is up, this has to be down. If this is down, then this has to be up, right? So in some ways, the entanglement reduced the number of possibilities from 4 to 2, but then that's what makes it also interesting. And now I can take interesting measurements from it and solve my math problem. To a very rough degree of approximation. That's how I understand it. But, maybe a good way to do this would be to explain like Shor's algorithm, or like the simplest possible quantum algorithm.
Yeah. It's so hard to do that with with the classical analogy, but I think where let's not do Shor's, let's do the quantum search algorithm, right? So quantum search is let's say you have roughly speaking a database of objects, right, in which you want to search for one with a certain property. Classically, for unstructured search, the complexity, so the time taken to search an unstructured database, the time taken is proportional to the number of objects in that database, right? In quantumly, the time taken is square root of the number of objects in that database. So it's called a square root speed up, right? And so if you look at how the algorithm works, you first start with a state in which you have a superposition. So let's say your search head let's say you have a search head, that will point at any object in the database. So that search head is in a superposition of all possible states at the same time, right?
So could you make it a little more concrete? That what objects are we talking about?
It could be anything. It could be anything, right? It's not
numbers. Let's take 64-bit numbers.
Yeah. Let's say let's say you have all numbers between 0 to n, let's say, or 0 to n minus 1, and you're looking for a number that satisfies a certain property, right? maybe the square of the number is equal to 64 or something like that, right? So you start off in a state where you have equal probability of finding any of the numbers, right? You have equal probability of that. And then you use a combination of operations where your quantum you're representing this superposition of probabilities, right? You can represent it as a vector, right? So you can say that you have 1 over n probability of finding if you measured at that initially, you have 1 over n probability of measuring 0, 1 over n probability of measuring 1, 1 over n of measuring 2, right? So you have equal probability of finding that head, right? Or of finding that head in any of the states, right? And then you use a combination of operations. So you basically start reflecting this vector about the correct, so if you look at how the algorithm works geometrically, it kind of reflects, it does a little bit rotation around this equal superposition state, then a rotation in the opposite direction of the correct state. So you kind of do this geometric picture is that you kind of do these operations, this series of rotations that gets you closer and closer to the target state, right?
Reminds me of binary search.
Yeah, but with a quadratic speed up, right? Classically, you could never get that square root of n, right? But quantumly you can. But the thing is, this is one way of understanding it, right? Not all quantum algorithms have this geometric picture, right? So if you see me struggling a little bit to explain like exactly how quantum algorithms work, it's because there's so many different ways of thinking about it, right? One can think, of course, of this geometric picture, but then again, if you think of how quantum computers are used to model chemistry or optimization problems, then you don't have this geometric picture anymore, right? So it's
I'm still back at the geometric picture. So
yeah.
Tell us a little bit more about how that specific one works. So how do you manipulate the distribution? Like maybe talk about quantum gates or like what's happening physically, like how does shining a laser change the probability distribution, or what exactly is happening there?
Oh, so at the physical level. Yeah, so okay, so when you theoretically, let's just look at this quantum search algorithm, right? You have this physical picture of of your quantum state, doing through a series of reflections, getting closer and closer to the correct answer, right? So it's doing a rotation, it's doing a reflection, a rotation around the equal superposition state, then the correct state, and it's getting closer and closer. To implement those operations, you need a series of logical level gates. So these are similar to like Boolean gates that you might have in classical computers, right? So similarly, you have these gates that implement quantum logic, right? But these gates again are just you can describe them with a matrix, essentially, that say what goes in and then what goes out. But next, then you have to look at your target technology, right? And are you using atoms? Are you using ions? Are you using superconducting qubits, right? And depending on whether your qubits are from Google or IBM or IonQ, right, you may be using very different technologies. And so basically all of these companies then provide a compiler, right, that takes this high level logic down to low level logic, which can be directly then translated into laser pulses, for instance, that can then kind of implement, like single qubit rotations or 2 qubit entanglements in order to execute the quantum algorithm. And so when you go to the physical level, right, then you have then you're really down to kind of writing, writing down an equation, or it's called Hamiltonian, that describes the atomic physics, for instance, right? The energy levels of the atom and which two levels have been isolated to act as the qubit. And then when it absorbs the photon, how does it drive the qubit into the next state? And with ions, for instance, you use what are called like motional modes of entanglement to entangle different qubits together. So actually, in quantum computing, many different kinds of physics are required, right? You need physicists that are looking at like material science or atomic physics, right? That's one kind of people who work at that level. Then another kind of work is just at the compilation level, right? So people who understand gate symmetries and try to design the best possible compilation routines for the different technologies. Then there are people like me who work more at the algorithm level, right? Try to design different algorithms. And then, of course, there are people who work more closely with the application area, right? Let's say you're trying to solve a differential equation or optimization problem. They figure out what would be the quantum approach for that problem. So it's also not one kind of like quantum physicist is like a very broad category nowadays. And people specialize. Yeah.
The thing that you said at the beginning, which is that we're searching for a number whose square is 64, right? Mm-hmm. How does that information get encoded into the quantum operations that you design?
Yeah. So if you look at the textbook version of the algorithm, they would call it a quantum oracle, right? And they won't give any details of how you actually implement that quantum oracle. But basically, what it simply is that you design like a logic circuit that would, let's say, flip the state of a target qubit when it finds the correct answer. Right, so you would actually, in this case, it's very easy. You would design a reversible logic circuit that if it finds the correct answer, it flips a target bit, and if not, it doesn't flip. But yeah, in this case, it's actually pretty classical. That oracle is completely classical, right? It's just that you will, when you implement it on this quantum state, it will kind of change all of the whole probability distribution at the same time.
I wonder if, again, I go back to the binary search thing. It's fully ordered, then I can do it in log n, to find something. What happened here if it's unordered to do this in root n?
So I think,
is there something that went on in this 2 to the power n states that all of a sudden I can do this in root n?
It's the destructive interference. It's that you're constructively interfering the correct answer and destructively interfering the bad answer. So
now you're taking me to the simplest thing that I've learned these days, reinforcement learning. There's something going on with good answers and bad answers to fine-tune models, I mean, I'm sure.
But that's classical, right? So you will never, no matter what you do, you will.
Is there without writing matrices, is there an easy way to explain things
can you write matrix for this? And is that the way it's working here too? I mean, are these matrix operations?
So at the very lowest level, right, when you have single qubit, most of the platforms, they work with single qubit gates and 2 qubit gates, 1 and 2 qubit gates. And for a single qubit gate, it's a 2x2 matrix, right, between 0 and 1. And for a 2 qubit gate, it's a 4x4 matrix, right? And that's at the very lowest level. right? But at the higher level, of course, you cannot describe the whole. I mean, if you could, in principle, write a 2 to the 64 by 2 to the 64 matrix to describe it, but it won't be very useful. So typically what, you have your higher level quantum operation, but you decompose it in terms of these 1 and 2 qubit gates when you send it to the quantum, kind of the quantum hardware, and that gets executed. But, typically, so, there is like nowadays we have what's called, people call it different things, but like a quantum assembly language, right? Where every API or every hardware platform provides a fixed set of operations that it can run. And then the compiler, designer, like basically the software people know to target that, right? So they give the user much more option in terms of like how they write their programs, but at the output, they produce only the set of operations that can run on a target hardware. So it is getting kind of standardized in that sense.
What about the physics of the computer itself? Like when you say physics, I mean the physical dimensions, like maybe just to visualize it in the next 5 years versus the next 20 years. Like what is your, maybe that's where we should end it, because at least it brings it back to the classical world, a little bit. And we'll probably have to do like many more episodes on this, because at least I told Amit that it'll take me 10 years to understand this field, But tell us about where we are with respect to the computer itself. Like, how big is it? How accessible will it be? When will it get in the hands of, this happened with Watson as well. Like, it was in the hands of IBM. And like, oh, this is AI computer, and you can't get access to it unless you pay $50 million. And all of a sudden, ChatGPT comes and says, here is an API, it's 1/10 of a cent, and you get AI. So how far are we from this ChatGPT version of a quantum computer?
Yeah, that one is, I think that's very instructive, right? So right now, the scenario is that most of the quantum computing, or at least several of the quantum computing companies, right, like IonQ or IBM, they have their quantum computers available over the cloud, right? So you can actually sign up for an AWS account, right, and go to AWS Quantum Cloud and access IonQ quantum systems, right? At the same time, I think the price point for all of them is quite high, right? And really, the people who would use it right now are researchers, right? Grad students.
Give us a sense for like what's the unit of?
It's not in US dollars. It's in Bitcoin plus.
Yeah, I think like if I'm correct, IBM systems charge you $1.6 per second or something like that they call it quantum runtime second, right? So they have some way of calculating runtime.
And how many qubits is that?
Well, their systems have a lot of qubits. Like I think they even have a system with 500 or more qubits, right? But the thing is that just because you have 500 qubits doesn't mean you can use all of them. They may not have high enough fidelity or high enough quality gates in order to kind of do a very large scale computation. So so at the physical level, we have these companies that have companies and research groups that have very different approaches, right? Like I mentioned a few, right? There can be atoms, there can be ions, there can be superconducting circuits. They can be even somebody is doing electrons on helium, for instance, right? So the substrates are very, very different, right? They have all kind of put some thought into how they're going to scale them up. So basically, we were talking about physical substrates for qubits, right? And so there are many different approaches, right? Like Intel, when I was working at Intel, and they still are pursuing this silicon quantum dots, right? They're trying to trap an electron in a series of quantum dots and use them as qubits, right? So everyone has different approaches. I don't think a clear winner has emerged yet, right? I think there are, in my view, a couple of key criteria which will influence which of these technologies becomes or qubit technologies becomes commercially viable. One is their scalability, right? Of course, you cannot, 20, 30, 40 qubits is not going to cut it. You need to build hundreds at least, if not thousands, right? And so, of course, kind of the physical footprint should be reasonable, right? You should be able to make them modular, right? So that, you can kind of have this vision of stacking them in a data center. They should not have some insane requirements that you need, like liquid helium refrigerator that is the size of a football field or something like that, right? So there are all these engineering requirements, right? The second, I think, is very importantly, quantum bits, they're quite fragile. So they're very sensitive to any kind of interference from the environment. So even, if a cosmic ray hits them, they can lose their state. Or, if there is a photon or something in the vicinity, or if there's some disorder. So if it's a solid state qubit and there's some disorder in the substrate on which it is built, then it won't have like high lifetime. So that's why you need quantum error correction, which is basically, you use several physical qubits to build what's called one logical qubit, which has much lower error rates, right? So
the first time I understood the reason for quantum correction, that you use physical qubits to actually
many physical to build one logical, yeah. And some technologies will emerge as being naturally much more amenable to error correction, because they will have inherently longer lifetimes, higher fidelity operations, and even things like connectivity, where you have the option of entangling a given qubit with many other qubits, right? Versus just maybe one or two other qubits. So I think these are all both scientific and engineering challenges, and not any clear winner has emerged yet. But it is good that so many people are pursuing so many approaches at the same time. So I'm sure that one of them will win out.
It reminds me of the nuclear fusion sort of.
No, don't say that.
I think in a good way. I mean, I'm sure you can go back to 2015 and say quantum physics can go around for 100 years. So it's not a bad place to be in. Nuclear has gone on for 60 years. But my thing is that in the next 10 to 15 years, both of them will have a breakthrough. Like a real,
yeah.
I mean, maybe we'll discuss this in a separate episode. I know today we actually rumbled a lot, but in a way it was about getting soaked as opposed to really getting organized in the way at least I understand things. We should probably think of what do you think of a next episode in terms of, should we look at compilers, the application? Like maybe we have to visualize this a little bit of how it even works in the industry. A little
Yes.
bit. So the layers that you spoke of, I'm pretty sure we can get to the physical layers through a Zoom call, unless we get to a wet lab or something. But what could we do to actually make this a little bit more real, if as and when we meet next time?
So yeah, that's a good question. Like if we put a layer of abstraction over all the physics and think like a computer scientist, what is the interface to this thing, and how do people who are writing code start using these things? That would be a really good one to understand.
Yeah. So the software stack is emerging, right? Like I mentioned, right now people are just, or at least so far, we're coding at the level of individual qubits. But of course, that's not scalable, right? You make so many mistakes, and it's hard to debug and everything.
It's
So
not accessible to most people, right?
Exactly. Even for me, right? Like I worked at IonQ, so I know ion traps a bit, but electrons on helium or photonic qubits, I'll have to spend 6 months studying that, right? So yes, you need a layer of abstraction, and some are emerging, right? Like this assembly language that I talked about, it's called QASM, is one of them, but then there's others, right? Um, you know, uh, you have these what is it called like IRs, right? In interface, these different interface definitions between different layers, and I think all of that is kind of just people have small attempts at those, right? But yes, you need everything. You need compilers, schedulers, mappers, libraries for different application areas, whether it's chemistry, machine learning, and then of course APIs that end users, let's say you're working at Hyundai and you want to use quantum machine learning for self-driving cars, right? How do you do that, right? So all of that is emerging. My company is working on a bunch of those. At least we have the ambition to kind of do that. And the space is wide open right now.
We didn't get to talk about your company at all. What is it called? And
This is the post IonQ. You started a company, right?
Yes. So my company is called Coherent Computing, and the goal is to make the rapidly kind of increasing capabilities of quantum hardware accessible to end users without them having to go off to do a PhD in quantum computing, right? And the first product of the company will be so what we're building right now is a framework to be able to train large quantum models, right? And we have some pretty nice initial results. And ultimately, I think, it's so early stage that I think the go-to-market strategy is still kind of open. But I think it might be similar to what ChatGPT is, right? That we have the capability to train large models, right? And we train models in different application areas, and then kind of let people access them, whether it's in material science or climate, etc. Yeah.
I'll ask one last question, which is, at some level of abstraction, I can visualize this, that there's a library that factors numbers. There's a library that runs each of the algorithms, has like an interface, which is very classic. Like you give this input, you get that output. And at that level, I don't need to know anything about how the quantum computer works. All I know is that I can give it very large numbers, and it'll give me factors of those numbers in much faster time than a classical computer. What's like just one level below that, so that I can recompose these capabilities into newer algorithms? Or does that require me to understand how quantum gates work all the way before?
No, I think the ideal would be that we give programmers the tools that allow them to reason about quantum operations. So you don't really need to know about low-level gates, but just like quantum logic things where you're controlling an operation on a group of qubits that are in superposition, or you're doing these operations that are called phase estimation, where you're estimating the phase of a quantum state that's evolving under some Hamiltonian. So just tools that you don't need to know the physics of the qubits,
and yet
but
the physical terms. I think he used a lot of physics terms in there.
No. So, but those are not too. There are not so many of them. There's just some. I don't know what else to call it, but quantum reasoning, which is a bit. How do you reason? How do you make a group of qubits do what you want it to do? Right.
I think we're still in 1970s when you have to load and store. Remember the assembly stuff? You're probably assembling all these things and saying, okay, understand superposition, understand entanglement, or look at these gates kind of stuff. I mean, do you think that's a good way to think about it?
So it's just like, like what are quantum data structures, right? So when you program in Python, you have vectors, you have lists, right? Or you have arrays, or you have this different kind of data structures which allow you to
manipulate state.
Yeah, right. So what are quantum data structures? What is quantum logic? All of that has still not completely emerged yet, right?
Is there,
And
paper, a document, or article that one can look at to know these quantum reasoning concepts?
Yeah. So I think the thing is that there is not anything that kind of presents it like that, right? It's just that when you start reading, when you start understanding how a lot of different quantum algorithms work, some structures start emerging, right?
And this
Right.
is the work that you're doing, basically.
Exactly. Some structures start emerging, and then you can think of having like a software framework that kind of implements these structures as first-class objects in the language, right? And then you can kind of use them as is, instead of having to re-implement them from scratch for every different algorithm. But it doesn't exist yet. So it's like 1970s or wherever. Yeah.
Well, when we were talking before the podcast was starting to get recorded, you'd mentioned something about maybe how the human brain works is also in a quantum way.
Yeah.
And the reason we brought it up is because I was reading this Jan LeCun thing for you, which is because he's arguing that, look, we need a massively large computer to even get close to the human level of sort of AGI and, I mean, real intelligence, human intelligence. So he makes a case for this, like, LLMs are 10 to the raise 13 tokens times 0.75 words per token times 2 bytes per token is 10 to the power 13 bytes. 4-year-old child is 16,000 wake hours times 3,600 seconds per hour to times 10 to the power 6 optical nerve fibers times 2 eyes times 10 bytes per second is 10 raised to the power 15 bytes. So in a 4-year child, in 4 years, the child has seen 50 times more data than the biggest LLMs. This is when he said, look, I know we're looking at this very classically from a data point of view, but who knows how the human brain works? Maybe there's quantum stuff going on, entanglements going on with neurons and things like that as well.
Yeah.
That just says something about how little we know about our brain too. And
Yeah.
OpenAI is actually even in the right state of mind to talk about AGI right now.
Yeah, I mean, typically what we would think is that, at the temperatures at which our body is, right, like quantum effects would be suppressed, right? But however, there are some serious physicists, including, I think, the person who heads up Google Quantum AI, who are thinking about this, what might be the mechanisms at which quantum effects or quantum correlations might play a role in the human brain. But there's no established science there yet, so it's still open area of research.
Awesome. Well, thank you so much, Sonika, for really sort of dumbing it down for me at least. I'm pretty sure we'll need many episodes of this because it's such a young and fledgling state,
It is very young. It's very new. Yeah.
But we look forward to talking about your company, and because obviously you're trying to make it simple enough and abstracted enough that classical people and businesses can use it as well.
Yeah, that's the goal.
Forward to actually seeing you back again, right, Amit?
Yeah, no, thank you so much, and thanks for taking time out from your trip in Europe.
Yeah, looking forward to learning more, and I'm gonna watch some videos as well, and maybe in this recording itself, we'll put some links to some videos that we actually watch, because I think this is one of the rare episodes we'll have to put some helper functions there. Some images, some videos, things like that as well. Thank you again.
Yeah, it was really nice talking to you.
Likewise.
Okay.
Thank you.